So now we've had an introduction to probability. In this video, I want to introduce some probability rules, and through those we're going to be able to come up with different ways to calculate probabilities, and I'll compare those actually to some that we saw in the last video. And I also want to give the definition of independence for events. So the first rule I want to look at is called the addition rule. And this tells us the following. The probability of A union B, and importantly, this just means or, is equal to the probability of A plus the probability of B minus the probability of A intersect B. And again, that just means and. So to keep this in mind, I think a lot of times it helps to use what's called a Venn diagram. So when I'm using a Venn diagram in probability, we usually draw some kind of rectangle to represent the entire sample space and circles to represent our events. So if I have A and B, then we can think about what would happen if we're looking for the probability of A or B. And importantly, if I talk about A or B, I'm really looking at anything that lies in either of these two circles. So it's going to be this whole shape here. Now, a common misconception is I'll see that people will leave off the minus the probability of the intersection. And I want to point out it's important that we're not saying that you can't satisfy the being in the union by being in the intersection. Of course, we can see that that's certainly true in my picture. The overlap of the two circles would be the intersection, and that does sit inside of the union. But instead, if I think about adding up the probability of A, I'm going to add up every outcome that sits in here. And if I add up the probability of B, I'm going to add up the probability of every outcome that sits in here. But notice what happens is effectively we double counted what sits in the intersection because we counted that with A and with B, but we only want to count it once. And that's why we then subtract one of those from that sum. So we want to remember that we have to subtract the intersection. So thinking back to the example that we ended with before, where we had the four-sided die labeled A, B, and C, and we were rolling that twice. One of the questions we looked at was finding, let's put it here, we were asked to find the probability that you roll at least one A or at least one B. So here's or. So employing this rule now, we could think about taking the probability that you roll at least one, forgot an E up here, 1A, plus the probability that you roll at least 1B. Minus, and I'll put it down here, the probability that you roll at least 1A and at least 1B. Now, to think about this, let's actually consider what the outcomes would be. So for the probability that you roll at least 1A, we saw actually in the last video that there were 7 of those outcomes. So it was AA, A, B, A, C, A, D, B, A, C, A, and D, A. I have a kind of a symmetric result for B. We could have B, A, B, 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 C, B, D, A, B, C, B, and D, B. So right now that's 14 outcomes. And then we have to subtract the overlap. And the overlap, I'll point out, is A, B, and BA. And if you're listing out the outcomes, we can see the overlap because these are the only two things that I listed in both blue and red. So consequently, the result would be the 7/16 plus 7/16 minus 2/16. And sure enough, we get the same answer we ended up with in the previous example. So that's just a demonstration of that rule. Often that rule can be helpful in giving you a more efficient way to compute certain probabilities. So the next rule I want to look at is called the complement rule. And this says that the probability of A complement is equal to 1 minus the probability of A. So first of all, what do I mean by A complement? I mean, we're getting this notation here. So when I have this C superscript, that's referring to the complement of the event A. And the complement of A is basically all outcomes in the sample space that do not satisfy A. So in my Venn diagram again, if I just focus on just one event A in here, if this is A, then A complement would be everything in orange here. So again, to kind of use this new idea in comparison to our example from last time, if we go back to the part where we wanted to compute the probability that you roll at least 1A or at least 1B, we can think about that in terms of complements by saying that this should equal 1 minus the probability that you roll no A and no B, basically. So that's describing the complement. And this is a little bit easier to envision because we just think of the only events that have no A and no B, and there's only 4 of those. So if we think about our sample space, we would have those. And again, we get the same numerical answer, 1 minus 4 out of 16, and we get our 3/4. So those are going to be 2 rules that we can rely on to help us compute probability. And in terms of starting to think about the and relationship between events, this leads to a discussion of what is called independence. So here we're going to say events A and B are independent if the probability of A intersect B, which again, remember that's and, is equal to the probability of A times the probability of B. So this is going to be our mathematical definition of independence. To give this some context, think of the following example. Flip a fair coin twice. Then one way we could represent our sample space. So again, we want to identify if the coin landed heads or tails. Let's use H and T for that. If we do this twice, the sample space includes heads, 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 tails, tails, heads, and tails, tails. So consider some events that I'm going to define below. These will be events A, B, and C. So A will be that the first toss is heads. Whoops. B will be that the second toss is heads. And event C will be the event that both tosses are heads. Now, once I have described these events, We can also identify the subset of the sample space that this corresponds to. So A is the subset HHHT. B is the subset HHTH. And C is the subset HH. Again, because we're assuming that this is a fair coin, we can assume that each of these 4 outcomes has probability 1/4 of occurring. So if I want to talk about the probability of A, that would be 2 out of 4 or 1/2. Likewise, the probability of B would be 2 out of 4 or 1/2. And finally, the probability of C would be 1 out of 4. So given that background, we can actually start to think about the notion of independence. In particular, A and B are independent. So they are. And the way that I can prove that is coming back to our definition. So the probability of A intersect B. The intersection of A and B has to include all outcomes that are in both A and B. So that is one outcome, that's HH. So computing the probability, just brute force as we call it, by actually counting the outcomes that fall into both A and B, I get 1/4. That's also equal to the probability of A times the probability of B here, right? That's 1/2 times 1/2. Because these two things are equivalent, that's enough for me to conclude that A and B are independent. A and C, on the other hand, are not independent. And again, this can be verified by looking at the definition. The probability of A intersect C, again, I look for things that lie in the intersection, so lie in both A and C. Notice that in this case, the probability of A and C is actually the same as the probability of C. It's simply 1/4 because the only outcome in the intersection is heads-heads. That is not equal to the probability of A times the probability of C, right? That would have yielded 1/8. So by showing that those are not equal, that's enough for me to say that those two events are not independent. So independence is going to be something nice. A lot of times you'll be given a context in which you can assume the events are independent, and consequently that's a nice way to take advantage of being able to multiply probabilities to get the probability of an intersection. If I don't have assumed independence, then I would have to treat the probability of my intersection by the brute force method of really kind of keeping track of the number of outcomes that correspond to that intersection and thinking about the probability of those outcomes.